In this tape, we want to describe how to precisely determine refractive indices on uniaxial minerals. So, as a point of review, just some definitions here. In each uniaxial mineral, we have what we call an ordinary ray, symbolized with O, and it has a refractive index omega. That is, that rays vibrating in this ordinary ray direction have a quantifiable refractive index omega. And conversely, there is an extraordinary ray whose vibration direction is parallel to the c-axis, which is symbolized by the symbol E, and whose refractive index is described by epsilon. Now, we use the immersion methods to determine the refractive index of the O and the E rays. And the procedure that we use in immersion is to orient the mineral so that we observe only O or E. And the way we do this is to use conoscopic view, or the interference figure, to help you with this orientation. So we make an immersion mount, we look at the interference figure, and then we decide where O and E ray is, and use the petrographic microscope to look at only the O or the E ray, and then measure them in relief in the same way as we've done previously. Now, the methods that we can use in which to orient the O and the E ray there really are three kinds of methods. First kind is called a random search method, and this is the kind that we're going to emphasize. In many respects, it's the simplest kind of orientation method to use. But there are two other commonly used varieties. One is called the spindle stage, and the other is called the universal stage. Now, the spindle stage and universal stage have in common the fact that you have the ability to rotate on several axes individual mineral grains. And this is a special kind of mounts which you can use in which to mount individual mineral grains or an entire thin section, in which you can actually move them in more than the single direction which is allowed by the ordinary microscope stage. Now, we're going to concentrate, and we're going to talk exclusively in this tape about random search kinds of methods. Okay, so what do you do in a random search? You make an immersion mount, and the first element of the immersion mount, that it has approximately 25 grains, and we use a small cover glass and grains that are relatively fine grain, something on the order of 50 to 100 mesh in terms of their grain size. And we put these 25 grains in the immersion mount, recognizing that they will have all different kinds of orientations. And so that we don't emphasize the ability of having to rotate an individual grain. Instead, we rely on the fact that given 25 grains, we're going to have one or two of those grains in the orientation that we need for whatever kind of a test. So, taking these things in an immersion mount, then we find the following procedure. We find the proper grain to measure the ordinary ray, and we test its relief relative to the immersion oil. After finding O, then we find the E ray and test its relief relative to the immersion oil. And then, depending on the results of steps 2 and 3, we repeat using a different immersion oil to see how the results will change. And we repeat this in an educated fashion, so taking advantage of our previous experience. Okay, well, I'm going to just take a quick look at an immersion mount here for you and show you our typical sort of setup. So I've prepared an immersion mount, and we'll just take a look at this mount now first in plain polarized light, and now with the polars crossed, so you can see these individual mineral grains. And these have all random kind of orientations, and so the point is to be able to find O and E in these randomly oriented grains. In nearly all the grains we can measure the O ray. In only a few of the grains we can measure specifically the E ray. So what about a strategy then for finding O and the E ray? First of all, to find O. O is the easiest one to find, and so the steps for finding it are a good deal simpler. You can choose any grain and look at the interference figure. And from that interference figure there will be some way in which you can rotate the mineral grain until O is parallel with the microscope polarizer. Now it depends on what kind of figure you have in order to find this kind of orientation. So let's go through the individual figures and review how the orientation procedure goes. First of all, what if you have a centered optic axis figure? Here's the centered optic axis figure shown schematically, and typically has this two isogyre kind of pattern and a series of color curves that are emanating out from the center of the figure. Now, you can't miss finding O with this kind of figure. The figure doesn't even change with rotation. This is the circular section of the indicatrix, and so this, any grain that shows this kind of figure in any orientation, you can measure O. So it's a cinch if you find this kind of figure. The only trouble is that these kinds of figures are not particularly common. A much more common kind of figure is the uncentered figure. And this is a schematic view of the uncentered figure. If you watch an uncentered figure closely, you will realize that as the figure moves, and what I've represented here is the field of view, which you have in this type of figure. But as the figure moves, you see successively traverses of both isogyres. Sometimes the center of the isogyre cross is actually within the field of view, and you can see this point, but many times it isn't, and you simply see the successive traversing of each of these isogyres across the field of view, usually in a perpendicular direction. And by watching this pattern, you can observe where the center of this cross is, even though it may be outside of the field of view. And so by rotating the figure in the proper sort of way, you can position yourself so that one isogyre is here, another isogyre is here, and you're really essentially looking at the northeast quadrant. And as you get the interference figure in this kind of orientation, then the O ray is always tangential to the center part of the uncentered figure. It always has this when you're looking at the northeast quadrant, the O ray is always oriented in the northwest direction. So then the procedure it would be to take out the Bertrand lens and the converging lens and simply to rotate the stage of the microscope so that the O ray is parallel to the microscope polarizer. Then you can measure uniquely the ordinary ray in terms of its refractive index. Now, in order to make this clear, let me just look at an uncentered figure, and we'll do the rotation so that you can see how we infer the northeast quadrant during rotation. So I'll go back to our microscope here and look at an immersion mount which shows an uncentered figure. And now I'll rotate the figure, and as I rotate the figure, I will indicate which corner the crossing isogyres is located. And so that as the figure rotates and as the isogyres traverse the field, you can, by watching the figure, recognize that, for example, now the intersection of the isogyres is in the northwest quadrant. Now it's moved over to the northeast quadrant. now it's in the southeast quadrant, now it's in the southwest quadrant. So I want to rotate it back until the intersection of the isogyres is all the way around again into the southwest quadrant. This puts us in the northeast quadrant of the orientation, and now I know that the O ray in this orientation is located in the northwest direction. So at this point I wanted to take out the Bertrand lens and the converging lens and simply rotate the stage back this way, and now I'm ready to measure the O ray exclusively in an uncentered figure. So that's the orientation procedure using an uncentered figure. Well, what if you have a flash figure? This is another common kind of figure, and we've already demonstrated the flash figure and the way that the isogyres leave the field very suddenly, and when they leave the field suddenly, they leave in the direction of the E ray. So to find the O ray is simply to use the direction that's perpendicular to E. So once again, once the isogyres leave the field, for example, in this northeasterly direction, I immediately know that the O ray is located here. I can turn back, look at the grain in plane polarized light, and rotate it 45 degrees until the O ray is exactly in an east-west position parallel to the microscope polarizer. Now I can test for relief on the O ray. Well, another thing that's very useful to know, of course, is the sign of the mineral. Now, the sign of the mineral can be determined with accessory plates, and I just want to refresh your memory about sign determination again. For example, here is sign determination for the common kinds of uniaxial figures, the optic axis figures, for example, the centered optic axis figure. And this is the indication of what the centered optic axis figure would look like on a, let's say, a grain of the mineral quartz. First of all, in the straight cross-polarized light, and second, with the gypsum plate. And you can see that with the gypsum plate, then you get addition of colors, and they change from white to blue in the northeast and southwest quadrants, and a change from white to yellow in the northwest southeast quadrants. An indication then of positive optic sign. The minute you know that the sign is positive, then you know that epsilon is greater than omega, or that E is the slow ray. If the figure is uncentered, then you want to do the same kind of trick as we did before, rotate the figure until we're looking mainly at the northeast quadrant in this particular case, and use the accessory plate, again, gypsum plate indicated here, and the addition of colors, change to blue color indicates that this mineral is positive. If this color was yellow, the mineral would be negative. Well, how about the sign determination on when you're dealing with the flash figure? You can also easily get the sign relationship. And the sign is determined this way. Again, you watch the departure of the isogyres. This gives you the indication of the direction of the E ray. The isogyres always leave in the direction of the E ray. Then in order to find out if E is the slow ray or not, you use your accessory plate in conjunction with the cross-polarized view and look at the mineral grain itself. Here are the outlines of this particular mineral grain. And this indication indicates that this particular mineral is negative, because given a white interference color prior to insertion of the accessory plate, the yellow color here indicates subtraction and indicates then that E is the slow ray, and this particular mineral then would have a negative sign. Well, it's important that you know what the sign of the mineral is right away when you're doing an immersion mount, because that tells you the relationship of epsilon and omega. There are two possibilities. In the positive mineral, of course, epsilon is larger than omega. In the negative mineral, epsilon is less than omega. And since we've gone now to the trouble of looking precisely at what the omega refractive index is, we've made its determination, its refractive index determination, by orienting the figure properly and looking only at the O-ray and testing the relief using the central illumination test, the Becky line test that we have demonstrated before, or using the oblique illumination test. The test is the same once the grain is properly oriented. But after we've tested the O-ray, we need to be able to test the E-ray, and knowing the sign of the mineral then tells us whether the epsilon refractive index is going to be less than or greater than the omega refractive index. So this is very valuable information to determine the sign early in this particular game. Now the other thing that we can use as a clue is the birefringence. Now the birefringence, if you recall, is simply a quantitative absolute value difference between epsilon and omega. And the reason why birefringence is important is that the higher the birefringence, the higher the interference color that a particular mineral will show. Now I can demonstrate this very easily. For example, I can go to a thin section of a sandstone. And this is a thin section we've looked at previously, but contains virtually all of the mineral quartz. And if we look at this now in cross-polarized light, you can see that the quartz grains, the maximum interference color that's shown by these quartz grains is still only a first-order white. And this is an indication that we're dealing with weak birefringence, that the birefringence for this particular mineral is less than about 0.01. That is the absolute value of the difference between epsilon and omega. Now, knowing the birefringence of the mineral grain is important, and of course it's influenced by the thickness of the thin section. But if we know that, then we know what kind of immersion oil to use as our guess for the epsilon refractive index. If it's a low or weak birefringence, as it is in this particular case, then we know that the immersion oil we're going to use to test the E-ray is not very different than the immersion oil that we use for the O-ray. Well, now I'm going to move to a different mount, this time a mount of a orthopyroxene. Orthopyroxene has a moderate birefringence, and this is shown up by the fact that the interference colors that are shown are now within the second order range. The maximums are reds, yellows, and blues that correspond to the lowest part of second order kinds of interference colors. This corresponds then to a moderate birefringence between a range of about 0.01 and a 0.025. That's the absolute value of the difference between epsilon and omega. Now, to illustrate higher birefringence again, we'll look at an olivine mount. And the olivines show strong birefringence, birefringence that's equivalent to a value of 0.025 to about 0.1. These are third order interference colors as a maximum. And finally, again, calcite, and still another mount. In this carbonate rock, calcite shows iridescent, very strong birefringence. Birefringence that's equivalent to greater than 0.1 difference. There are rare kinds of minerals, for example, rutile, which show birefringence that's still higher, what we call extreme birefringence of 0.2 and higher. Extreme birefringence is rare and restricted to only a few particular kinds of minerals, rutile being an example. So then, just as a refresher, we look back at this interference color chart and show the boundaries here between the different kinds of birefringence, low or weak birefringence, down in this first order color range. And as soon as we reach here, this blue in this kind of range, we're talking about moderate kinds of birefringence within this range is shown, for example, by the orthopyroxene. Strong birefringence within the olivine range. And finally, way off the end of this scale would be the very strong and extreme birefringence that is shown by calcite and rutile. Now, this kind of application of using the interference color as an estimate of the birefringence works best in thin section. And in immersion mounts, there's always considerable variation between the thickness of one grain to another, so the birefringence criteria can be used with a bit less certainty. But if we make an estimate of the birefringence, and if we know the optic sign of a particular mineral, and we have already gone to the trouble of making an estimate of the omega index, then we can make an assertion about epsilon. And we should be continually trying to refine our estimate of epsilon as we go through the immersion exercise. And here's an example. For example, supposing that we have, through repeated application of immersion mounts, identified by matching the oil with the index of refraction, the omega index in a particular mineral. And we know that this omega index is exactly equal to 1.580. We can also very easily take the sign of any uniaxial mineral. In this particular case, it's a positive sign. Since the mineral is positive, we know from this bit of information that epsilon is greater than omega, that E is the slow ray, and that the epsilon refractive index will be higher. Furthermore, if we can make an estimate of the birefringence, and in this case we say that the mineral has a moderate birefringence corresponding to this range, then by simply adding this range to our omega index, we get effectively an estimate for the epsilon index. In this particular case, then, we know, even without directly measuring it, that epsilon has to lie between 1.590 and 1.605. And this then gives us a place to start in our immersion test for epsilon, which is much harder to find than omega. Okay, well, what is the strategy then for finding the extraordinary ray? Okay, to find the E ray. Well, if we know omega and the optic sign plus an estimate of birefringence, this allows a guess for epsilon. And so if we mount in a new oil, then our strategy is to identify grains that might give the E ray by looking at their relief. Now, the idea here is that if we have made a guess already for epsilon, and if epsilon is considerably different from omega, then when the omega index is being measured, or when the O ray is being seen by the microscope, the grains will have higher relief than will those grains which are properly oriented to show the E ray. This means that what we do then is to look for mineral grains that seem to have the lowest relief within our new mount. Now, for example, we'll do this. We'll make an immersion mount now in our new oil, which we've selected, hopefully to approximate the refractive index of epsilon. And we take a look at these particular grains. Here we see a series of these grains, and you can see that in any particular orientation, I'll just stop now looking at these in plain polarized light. Some of these grains show quite significant relief. That is, their boundaries show up very nicely. Other grains show rather low relief, and even a few of them show color fringes, where you see effectively colored edges on the lines of these minerals. Now, these grains that showed the relatively low relief are much more likely to be good grains in which to find E. So we would select some of these grains and use these grains to see if they show the right kind of interference figure. Now remember, what we're looking for here is a flash figure so that we can uniquely isolate the extraordinary ray. So we're looking for grains that have significant birefringence that certainly show significant retardation, but the best way to find them in this kind of mount then is to look for the ones that have a low relief. Now once you find the grains with that show the flash figure, then the procedure is to look at the figure and do the rotation of the figure and watch the position in which the isogyres leave the field. And the position in which the isogyres leave the field effectively locate the extraordinary ray. And that's an important kind of orientation. This is the only figure where you can look at the E ray by itself and measure epsilon by itself. So once you find this orientation on the particular mineral grain, then you want to take out your Bertrand lens and your converging lens, look at the mineral grain, uncross the polars and rotate this 45-degree position to parallel with your microscope polarizer. Then you can make the central illumination test or the oblique illumination test to determine the epsilon refractive index. Just a summary then of the finding E is to test likely grains. These are grains that we've already determined to be likely by looking at their relief relationships, by looking at the interference figure. You want a centered flash figure. And once you get the centered flash figure, you can find the extraordinary ray by looking at the direction in which the isogyres leave the field as you rotate the stage of the microscope. After you've seen the isogyres leave, then you look at the grain again in plane polarized light and rotate the extraordinary ray until it's parallel to the microscope polarizer. Now, an easy way to make this orientation to make sure that the E ray is parallel to the polarizer is to watch extinction on the mineral grain. And that is, you can, after you've seen the isogyres leave the field in the correct direction, then you want to look at the mineral grain in cross-polarized light. Take out the Bertrand lens and converging lens. Look at it in cross-polarized light and rotate that mineral grain until it gets to extinction. And if you've rotated in the proper sense from the northeast to the east-west, then you know that the E ray is precisely east-west, parallel to your microscope polarizer. Okay, well, just a summary then of our determination of refractive indices. First thing you want to do, determine the omega index. Why do you do that first? Because it's the easiest thing to do. Any mineral grain, if you orient it properly, you pay attention to the interference figure, allows you to determine omega. So you go through a series of immersion mounts, applying the central illumination test, the oblique illumination test, until omega is nailed down. Then you determine the optic sign. And from the optic sign, that will tell you whether epsilon is less than or greater than omega. You estimate the birefringence, and this will give you a very good guess as to what the epsilon index is, and you can start then with your guesstimate of the epsilon index and look for flash figures by finding likely grains and then testing them by looking at their interference figure. Now, the relief test is a very powerful way to identify uniaxial minerals. It's the best kind of criteria because uniaxial minerals have a tremendous range in their refractive indices, in their birefringence, and of course they have the possibility of being either optically positive or negative. But when combined with the other properties of the mineral, it's usually possible to make an unequivocal demonstration, identification of a particular mineral from its optical properties. So here's a list then of the optical properties of uniaxial crystals. The form is important, particularly the form within the different crystal classes, tetragonal and hexagonal classes, whether there is a rhombohedral kind of shape to the crystal. The color is important. Some minerals have a color which applies uniformly to them. Others have a pleochroism, which is a change of color depending on the differential absorption due to the different vibration directions of the crystal. Cleavage can be important. There are various kinds of cleavage, pinacoidal cleavage, rhombohedral cleavage that can apply to uniaxial crystals. We talked about various kinds of extinction, symmetrical extinction, parallel extinction that can apply in uniaxial crystals. We talked about birefringence and the fact that birefringence varies considerably among these different kinds of crystals. Optic sign, whether it's positive or negative, splits the uniaxial crystals into two groups. What kind of elongation exists? If the mineral grain is elongated, does the slow direction correspond to the direction of elongation? There's a possibility then of different elongations occurring for uniaxial minerals. And finally, of course, in the last case, the thing we talked about today, and the most diagnostic criteria are the refractive indices epsilon and omega that apply to uniaxial crystals.